Okay, so perhaps let's wait for a couple of minutes.
Sure.
People will join in YouTube and also via Zoom. Okay, welcome everybody to this week's Majorana-Raychaudhuri seminar series. Today we are delighted to have R. Krishnan from IFAE, Barcelona, Spain, and he's going to talk about using group extensions to construct flavor symmetric models. So I will send you a reminder when 5 minutes are left.
Okay. Yeah. First of all, I thank the organizers for inviting me to this lecture seminar series. It's wonderful to be a part of it. My name is Krishnan. I'm a postdoc in IFAE in Barcelona. So before I go to the talk itself, let me first explain the title of the talk. So this is about using group extensions to construct flavor symmetric model. So first of all, what are these flavor symmetric models? So I'm sure that you're all familiar with the Higgs mechanism. So the elementary particles in the standard model obtain their mass through the Higgs mechanism. Now, different particles have different masses. So the Higgs mechanism itself, it doesn't explain why different particles have different masses. And that comes from the Yukawa couplings in the standard model. So if a particle has a larger mass, it means it has a larger Yukawa coupling. Now, in the standard model, these couplings are ad hoc parameters. So you measure the mass, and then that would fix the coupling itself. And you don't have and the flavor symmetric models, these are attempts to explain how the Yukawa couplings got the values they have. So that's the basic introduction of these models. And there are several ways to do that. And what I'm interested in and what I mostly work with are the classical type of flavor models where you use more fields. They are similar to Higgs fields, and these fields are called flavons. And then, and again, the mechanism is similar to the Higgs mechanism. You write the potential, and then you get a vacuum expectation value by spontaneous symmetry breaking, etc. But the key difference is that in the case of Higgs mechanism, you have a continuous symmetry, which is the gauge symmetry. But for these flavor models, we use most cases discrete symmetry. Now, you can think of this from what we know from the Higgs case. So we have like a Mexican hat kind of potential, right? So it has this continuous symmetry. It's like the case of a hat, it's like a circle. The minimum is a circle. Now, if you go to this discrete case, so you can think of instead of a circle, maybe you have a hexagon. So if you write a potential with a field with this kind of a discrete symmetry, then instead of the minimum being anywhere on the circle, you get the minimum of that potential in the vertices of the hexagon, if you're starting with the hexagonal symmetry in the beginning. So that's how these flavor symmetries are used. Now, the second part of the talk, the title is how to kill two birds with one stone. So basically, what are these two birds? So this is something I want to talk about a little bit. So as I said, in this kind of flavor symmetry mechanism, we are using a finite group, a discrete group. And you write the potential, you minimize the potential, you get a vacuum expectation. And it is aligned in some direction like the vertex of this hexagon in that example. But in all models, it so happens that you always have to use multiple fields, several fields you have to use. You can think of, let's say you are modeling your quark sector, right? You have up type quarks, 3 up type quarks, and 3 down type quarks. So in that case, you will have to associate at least a field for the up-type quarks, another kind of field for the down-type quarks. All these are flavor symmetry fields. And then you have to write the potential. You have to minimize the potential for both of these fields. And then you have to find the minimum, which would become the vacuum expectation value for each of these fields. Now, the fact is, when you do this, if you have to get the correct alignment, which gives you a result which matches with the experiment, these fields have to be aligned in a discrete way, but also in a different way, in the sense that one field has to align along one vertex of the hexagon, for example. The other field has to align along another vertex. This distinction must be there, otherwise it doesn't work. And this is a problem because if you have two different fields, if you write the general potential involving both these fields, you have to write terms which couple both these fields together. And as soon as you introduce these coupling fields between the different fields, it will destroy your construction. So you cannot get this distinct alignment for two different fields. So this is a problem, and people have put forward solutions, but these are kind of, I would say, rather too much of an assumption kind of thing. For example, people say that they don't talk to each other, these fields are separate because they live in two different dimensions or something. So you have to introduce extra dimensional framework for this. So it's a difficult problem. And what I'm trying to say is that this particular framework group extension will solve this problem. So that is the one bird I'm getting. And what is the second bird? And this is more like a practical issue. So this and my emphasis is in neutrino models, and the neutrino experiments. They started to give good measurements from late 90s, early 2000, etc. And at that time, the measurements were not very precise. So theorists could come up with models which would give you uh, results which would match with the predictions which would match with the experimental results. But over time, currently these numbers are the neutrino masses and neutrino mixing observables. These are measured with a lot of precision, and it's very difficult to actually construct a model to match with these. So this is the second word I'm talking about. So if you do this group extension framework, yes, you can do both those things. So that's the brief introduction. So this is the research done on this topic so far. You can see it's pretty limited. Of course, if you look at the flavor symmetry literature itself, you have several thousand papers on that. But what I'm talking about is a very subset of that, of using group extensions. So you can see that half of these are my papers, and initially there were these three works. So this was done in early 2010. And these papers showed that if you use group extension, then the first problem I talked about, that means the dangerous bad cross couplings between different fields, that can be avoided. So what they showed was that you don't have to assume that there is a extra dimensions, and then different fields live in different dimensions, etc. That's not needed. You can do it in a much simpler way. So this is what they did. And then I took up this kind of construction, and then I had a different motivation for this. And this was the second motivation, that when I was towards this time in 2020, at this point of time, you have a very precise measurement of these neutrino masses and the mixing. So therefore, I found that this kind of construction helps us to make these precise predictions. Then I have also a couple of papers. This deals with the mathematics of this construction, because it involves some amount of complicated group theory, and also the minimization procedure and some topology and all that. So I don't have time to do that, but I may mention a little bit of math towards the end of this talk, if time permits. But most of my talk today is going to be this particular work. So this is a specific neutrino model. So it's like an example of this framework. So it would be nice to go through this example and learn various concepts. So this is what I will be doing. So this example demonstrates both. This shows that you can get really good predictions for neutrinos using this group extension technique. And also it prevents bad cross couplings between different fields. So this is what we are going to do. And before again going, I am taking a lot of time introducing things, but my apologies. But before going to the structure of the talk, let me give you a sneak peek here. So this values that you're seeing here, for example, in the left, this is something called reactor mixing angle. You can measure this number from neutrino experiments. And this one, second one, is called a solar mixing angle. You can measure that also. And these are masses of the neutrinos, M2 and M3. The red numbers that you're seeing, these expressions, these formulas, these are derived in this particular model that I'm going to talk about today. So you can obtain these numbers using whatever the group extension and flavor symmetry model, you can get it. And now you have a table here. This table shows the measured values. This is from a global fit done by a Spanish group, I believe. And again, you have this reactor angle here, and this is the 1 sigma value of this. So the value is 0.022000 plus or minus this. You can see how precise the measurement is. So they first measured it in 2012, and now this is very precise. And this red number, 1/3 sine squared pi by 12, the numerical value is here, 0.0223. You can see this is a nice agreement with this. Right? So it's a good, it's a success here. And the other one, solar mixing angle, the measured value is 1 sigma error. Within 1 sigma error is 318 plus or minus 0.016. And if you compute this number, it turns out to be 0.318. So again, it's a very nice prediction. And the last one, which is I'm most excited about, is the ratio of the neutrinos. The measurements, they themselves doesn't directly measure it. They measure this particular quantity. And that's like that. I mean, mass square difference is what they measure. And you calculate it, and the measurement is 0.1715 plus or minus this. And if you find this ratio, it is again 0.1716. So it's again in good agreement. So yes, so I'm hoping that you are impressed by this kind of prediction. That would give you motivation to try to learn and understand this group extension framework I'm going to present today. Okay. So yeah, this I explained. So this is going to be the outline of the talk. So in the first section, we have this model that I talked about. And I believe that, and I would like to go really slow. So taking these are a lot of new concepts are there. So I don't want to rush through it. So probably I will have time only to do this first part, which is the construction of the model and to get these highly precise numbers which match with the experiment. So this is actually one bird with that stone. And the second part of the talk, if time permits, this is about this other part. Like it's more mathematical part of it. Like if you write the potential and if you minimize it, the cross couplings are prevented, or the effect of cross couplings doesn't arise here. So this is the second part of the talk. I don't know I can cover that, but this is how my talk is going to be structured. Okay, now let's dive in. So as I said, we are using a discrete group. So discrete groups are groups with a finite number of elements, and these groups are generated by things called generators. So the group what I'm going to discuss is called a binary octahedral group, and this group can be generated using two generators, and I'm naming them as capital T and capital R. So what are they? So if you know the basics of group theory, you know that for any group you have you can have several representations. So for this group, what I'm going to talk about is a doublet representation, which I denote by this green 2. So it's a doublet representation. For this specific representation, the generators T and R are given here. So this is a 2 by 2 matrix. It's a 2 by 2 unitary matrix, and R corresponds to this, another 2 by 2 unitary matrix. So this is the doublet representation of the binary octahedral group. And this tau and tau bar that you're seeing here, they are the 8th root of unity. So the values are here. Okay? So this corresponds to a line at 45 degrees. So that's the 8th root of unity in the complex plane. Now, if you take these two matrices, unitary matrices, and then multiply them together as many times you want, then you can show that if you do that, you cannot get more than, you can get only 48 elements. So the total number of elements, total number of matrices that you can obtain by multiplying all these together, however many times you want, is 48. And that is our group. That group is called binary octahedral group. So that covers the basic. Next, okay, once you have a representation, one of the first things that you do is finding a tensor product expansion. So in this case, if you take this doublet representation and find the tensor product, what you are getting this is this 2 into 2 is 3 plus 1. Now I want to remind you something which again most of you would be familiar with, is the tensor product expansion of SU2 group, right? And if you take SU2, you have a 2 cross 2 equal to 3 plus 1. And 3 would be a real representation of SU2, and which is actually homomorphic to uh, SO3 group. Basically, it's the the mapping from SU2 to SO3. This is you are familiar with. And here again, you are seeing complex 2 by 2 unitary matrices, right? So this is a subgroup of SU2. In fact, a discrete subgroup, a finite subgroup of SU2, because SU2 has infinite number of elements. Here it has, as I said, it has only 48 elements. So it's just a finite subgroup of SU2. And when you get this tensor product expansion, 3, if it's the SU2 case, it's an infinite group, you will get SO3. But here it would be again a finite subgroup of SO3. And that I am going to show here. Oh, by the way, now I have to also explicitly show the tensor product expansion. So you have this doublet, this is 2, and then you take 2 of the doublets, XX, and obtain a triplet. So this is the specific formula. This is from the tensor product expansion. It can be done with standard group theory techniques. So you get 3 components. First one is x1 square plus x2 square. Second one is this. Third one is this. That's it. And in terms of the matrices, the generators would look like this. This is a 3 representation. So this is a 3 by 3 unitary. It's not unitary, orthogonal matrix because it's a real representation. 3 by 3 orthogonal matrix, another orthogonal matrix. Again, you can take these generators and multiply them together as many times you want, and you get a discrete group. And it turns out that in this case, it is 24 elements, which also makes sense because if you know SU2 is a double cover. So SU2, for 2 elements of SU2, there exists 1 element in SO3. It's something like that. So you have 48 elements in the doublet representation and 24 elements in the triplet representation. So that's the basic starting point. So this group is and this group it's an important group in the study of finite groups. This group is the symmetry group of a cube because we are in a 3-dimensional real space. So the symmetry group of a cube is called S4 group. So what we have got here is S4 group. Next, I mean, in physics, always you construct invariants. So I'm going to construct an invariant. And what am I going to use? I'm going to use a doublet. So x1, x2, and then a triplet. So it has 3 components, phi 1, phi 2, phi 3, which transforms as a 3. Now, from 2 of these doublets, I can get a triplet, which I showed in the previous page. And then I can couple this triplet with this other triplet and get an invariant. This is written here on the left side. So the triplet obtained from X doublets and phi, they couple together. And here I have written that in the matrix form. So again, I can just find the dot product of this guy with this guy and expand it. And that turns out to be exactly this. The reason why I am writing it in this matrix form is because we are going to model something and get mask matrices. So ultimately what you're seeing in the center becomes a mask matrix. So that's the reason why I'm writing in this matrix form. It's easy for you later. Okay. Now there is the problem is there are several nuances in the construction, so I have to explain each of these. So one of the things is in these modeling of the flavor models is that you introduce a CP violation, because this is an important aspect of it. We want to know if there is a, if the case of neutrinos, we want to know if there is CP violation in the charged electron sector, neutrino sector. So if you are modeling something with the neutrino masses, etc., you also want to model the CP violation with it. So you have to introduce CP symmetry, and then also you have to introduce how, you have to explain how CP is broken. So this is an important aspect of it. So I have to introduce CP symmetry into the whatever flavor symmetry I'm talking about. So this is what I'm doing here. And again, this is technical, and if you have done some work in this field, you know that in this kind of situation, we cannot simply introduce CP. We introduce something called a generalized CP. So if you're simply thinking about CP, just the complex conjugation of a scalar field. In generalized CP, it would be something more than that. I can explain why it is so briefly, if it's possible. So I have this invariant here, written again in a slightly different way. And you have the left guy here, the right multiplied here, and the center part here. In between, I have this I sigma y multiplied on both sides. Okay, so they are inverse of each other, so they cancel each other. So ultimately, this is exactly the same expression as above. The reason why I write this is that if you find the complex conjugate of the central part and then multiply like this on both sides, then what happens is the conjugation of this I, because there's i's here, that would cancel out, and you would get only the conjugation of phi's. So you compare this expression with the above expression. It's just the complex conjugation of the scalar field phi1, phi2, phi3, and the i's remain just unaffected. So that's the reason. So I want to define CP in such a way that for the triplet field, it's simply complex conjugation, nothing more. But that means for the other fields on both sides, it should be something more than that. So it's complex conjugation along with this multiplication with this polymetric. So this is, again, this is a standard stuff. People do similar standard stuff people do in flavor models. So that's all I am doing here. So first I have introduced the flavor symmetry group. Now I have introduced the how to do the CP part of it. Okay. Now let's go to more specifics of the model. Let's look at the neutrino sector, neutrino modeling itself. So in the neutrino modeling, mostly people assume something called seesaw mechanism. So in seesaw mechanism, you assume that there are, we have not observed them yet, so but we assume that these right-handed neutrinos exist. So in this particular model, I'm assuming that a pair of right-handed neutrinos exist, and I'm calling them N1 and N2. So the pair is N, which is again assumed to transform as a doublet of the binary octahedral group, which we introduced earlier, right? So that's the starting point. So you have a doublet of right-hand neutrinos which transform under the discrete binary octahedral group. That's the starting point. And then these are like the Higgs kind of fields. These are flavon fields. So I'll call phi, which has 3 components, phi1, phi2, phi3. And I assume that this also exists. And it has 3 components, right? So as I said in the previous slides, now with this, I can construct an invariant with two pairs of right-handed neutrinos and phi. So that's what I will do. But again, there are a couple of things I should say here. So for that, let me first make this table here. So I have 2 fields here, the neutrino field and the scalar field in the row. And in the column, I have the generators. So as I said before, the binary octahedral group is constructed with 2 generators, T and R. And these are abstract generators. These are the representations. So T2, these are 2-dimensional representation. The second one is 3-dimensional representation. Now, the next point is complexification. This is something I kind of didn't say yet, because when I started, I said that you have this connection from SU2 to SO3, and then I am finding the discrete group of subgroup of SO3, which is the discrete group of the cube. the S4 group, etc. But it is living in the real space, right? So 5 1, 5 2, 5 3 are real numbers. So there is no meaning in saying the complex conjugation of that. So I cannot, there is no point in saying 5 1, 5 2, 5 3 getting complex conjugated. So that doesn't make any sense. But then I want to, model CPU violation, etc. So it's important to introduce that. So to do that, okay, I have to again, broaden my scope. So I have to make these 5 and 5 to 5 3 fields into complex fields. So which is what I call the complexification. So that I have to do. So for example, I would say, okay, phi gets transformed into I multiplied by phi under some generator. So then it becomes complex. So that is done here. So I have that generator also in the table. So yes, so we have the original group, so binary octahedral group. Then I complexified it. Finally, I introduced the CP, generalized CP. So this is the setup. Now with the setup, I construct the invariant. So the invariant is two doublets and n a triplet, then dot product with phi and its complex conjugate. So this is our Lagrangian. This is the mass term, if I say so. And I have explicitly written the mass term here. So this expand this in the matrix form. It would look like you have the neutrino pair on both sides and a matrix in between. And this is actually what is going to become our Majorana mass matrix. And of course, in the normal sense, the Majorana mass matrix is a constant matrix. But here they are not constants, they are fields. 5 and 5 2, 5 3 are fields. So they become constants when your spontaneous symmetry breaking happens. So these fields acquire a vacuum alignment, and then you substitute these fields with the vacuum alignment, then it becomes a constant matrix. And that matrix is my Majorana mass matrix. So this is the idea. Okay. Whatever I have said until now, I would say more or less it's known in our community, flavor physics community. Of course, that particular group and the construction is what I have done. Other than that, the general concepts are known in the community. But what I'm going to do is the new stuff, the extension of the group. So that is what we are starting from this slide onwards. So this is from the previous slide. So we have phi put in this matrix form. It's a triplet. And how this phi transforms put in this table. Now what I'm going to say is that, well, I'm going to say that this phi itself doesn't exist. Rather, phi is constructed from some more elementary flavons. So phi itself is not elementary. So it's composed of something else. So this is the construction here. Oh, sorry, I have one, I forgot. So I will just repeat what happens to phi under these. So under T, phi gets multiplied with these 2 by 2 matrices. Under R, again, it gets multiplied. Under Z, it multiplied with I, so it gets complex. And then you have generalized CP. So it's just a repetition of what we saw earlier. Okay, now how is phi I am going to be constructed? Phi is constructed using three other fields, and I call them phi A, phi B, and phi C. And these are my elementary fields. And phi itself is constructed with these. And these are all doublets. If you look at this matrix, these are put in matrix form, but inside you can see what they are. So you have two components. So phi A has two components. Phi B has two components. These are less complex conjugate of that. And phi C has two components. So I have three two-component fields put in this matrix form. And then I say this phi I defined earlier, that is actually a symmetrized product of phi A, phi B, phi C. So this is the point. So phi A, phi B, phi C plus its transpose, that is phi. Okay, this is my definition. I'm going to say that this is how it is constructed. So now you'll understand, later you'll understand why. So with this construction, I'm going to redefine how these group elements are going to affect phi A, phi B, phi C, because we already know how these group elements is going to act on phi. But instead of phi, I'm replacing phi with phi A, phi B, phi C. So now I'll explain how are they going to act on phi A, phi B, phi C. So for that, okay, let's look at phi. What is happening to phi? On both sides, this t goes, right? So here also, both sides, the t goes. So on the left side of phi A, T goes, on the right side of phi C, T goes. Nothing happens to phi B, the middle guy. So that is how I'm going to redefine it. Now I remake the table again. So in this table, instead of phi, I have this the more elementary things, phi A, phi B, phi C, and then I tabulate it. And as you can see, nothing is happening to phi B, so it's trivial one. Next generator, R. What is happening on both sides? R is acting. Here again, both sides R is acting. Nothing is acting on the center. So I again tabulate it. So what is happening on N? Phi A, phi C are there, but phi B, nothing is happening. Next is the complexification. So the whole thing is multiplied by I. So what I'm going to say is I'm going to say the right side is getting multiplied by I. This is again, it is my construction, so I can say whatever I want. So the right side is getting multiplied with I, but there is a problem because if you take this is the matrix, and if you simply multiply this whole thing with I, it will no longer be in this particular form. So you started with the form, it should be form invariant, so it shouldn't change. So there's a problem. So and to solve it, I can, but what I do is I left multiply with this polymetrics. So if I do that, then it will keep the form. So I'm doing that now again. So then I have to multiply the inverse there because it has to cancel each other, because the whole object is to be multiplied with I only. So I introduce that on the right side of phi B. Again, now I'm going to tabulate it. So what is happening here? So phi A, nobody is acting on it. So phi A is trivial, action is trivial. The other two, you have the corresponding matrix, the group transformation. And I do the same with the complex conjugation. I'm going to repeat that so that you get here. And the final point, that's the most important point, which is the group extension part of it. That is this. So what has happened here is phi itself, nothing is happening there. But in the product, I am multiplying in between these matrices with something, some other unitary matrix. The matrix itself is given here. So these are some faces and zeros. So I'm going to do this. So what is happening here? So these cancel each other so that the whole object is unchanged, but the elementary object themselves get transformed under this guy, under X. So I'm calling this generator X. So under X, the internal ones are getting transformed, right? N is the neutrino, which is something that couples with phi itself, and it is unaffected. So that is 1. So let me summarize this. So I have started with this table with right-handed neutrino and a fly-on field phi with group transformations defined in this. Then I have come to this enlarged table where phi is replaced by something which I call more elementary phi A, phi B, phi C, and redefined how these group generators act on them. And after that, I introduced a new generator which act only on them and cancel each other so that it doesn't affect phi as a whole. So this is the whole process of group extension which I'm talking about, and why I will do it, etc., etc., will be clear later. And here is a more mathematical definition. If you are inclined to it, I would skip fast through this. Basically, what I'm trying to say is that the original group is this guy, GR, and this is something extra, and this is the larger group. This is the extended group. And the fermions, they see only this. But the larger group, everybody, the internal guys see the larger group. So that's the thing. And in mathematics, you call GX, the extension part, as the kernel, and this is the quotient, etc., etc. But maybe we don't have time to go there. Okay. So we have now introduced three fields, which I call the elementary ones. Now this next step is, okay, I have to write the general potential with these fields. Then I have to find the minimum, and then I say that these fields fall into those minimum, which is of course the spontaneous symmetry breaking, and that becomes the vacuum expectation value. And that itself involves several steps, and I would skip that, and then I would say that you have to believe me, I do that correctly, and then I get these as the vacuum expectation values of these fields. And yes, if you write the general potential of these and minimize them, you will get these as specific, as one of the discrete minima of that potential. It is there, so you can check it in the, or you can read the paper. So you can get these minima, and next step is to substitute these in our original mass matrix. So this is what I'm doing. So your Majorana mass matrix is obtained by substituting these vacuum expectation values back into this expression of the symmetrized product. And here we are. So this is my Majorana mass matrix. So all the circus I did earlier was to finally obtain this particular mass matrix. And this matrix has this information that I want about the mixing of the mixing angles of the neutrinos, and also of the neutrino masses. So most of the information is in this. Yes, and one thing you can do is this, you can compare with this original mass matrix expression I had with phi 1, phi 2, phi 3. Right, and then you can extract the values of phi 1, phi 2, and phi 3 by comparing these two, and the extracted values are written here. The three components, the first component is this, second component is this, third component is this. It looks pretty complicated here, but the original point was that, this is the group of the symmetry group of a cube, right? And if you write the potential of the symmetry group of a cube with that, then if you minimize that potential, you will not get something like this. You would get a minimum at these very nice points like the vertices or face centers or edge centers. That is all places where you can get a minimum if you write the potential of a field which transforms as the symmetry group of a cube. But here what you have got is something much more complicated. The reason that you got it is because you said that, well, phi itself is not elementary, rather it is composed of some other fields which are more elementary, and they have more transformations available to them, which is something that I added by doing this group extension. And because of all that, I got this complicated alignment. Because of that, I got this particular mass matrix. So that is the whole story. Now this is the Majorana mass matrix, and if you want a full model, you also have to construct the Dirac mass term and the Dirac part of that, and then you have to construct the charge lepton mass matrix. Then each of this will have several steps like that, and that would take the same amount of time. So I will skip through all of that. So I have to construct the charge lepton mass matrix. I have to construct the Dirac mass matrix. Then I have to construct something called a seesaw mass matrix, which again some of you may be familiar with, which is having this formula. Then I have to substitute and all that. And I will not do it, but rather I will just concentrate on this, which is because that is what I constructed right now, the Majorana mass matrix. And you can diagonalize the Majorana mass part only in this particular form with this pi by 3 rotation, and you get diagonal values, which is the eigenvalues, as root 2 minus 1 and root 2 plus 1. This turns out to be later the masses of the light neutrinos. So which is what I said, which I'm very excited about, and which I showed you in one of the earliest slides, where I compared the values with this prediction with the observed masses, observed experimental observation, and it turned out to be really good agreement. So that's coming from here. And this is the full expression of what you call the PMNS neutrino oscillation matrix, and you get this final result with theta equal to pi by 12, which would give you the correct reactor mixing angle and the correct solar angle, etc., which again I showed in the first one of the first slides. So I have skipped a lot of things because there is not much time here. Okay.
We have 7 minutes left.
Okay. Yeah. Sure. It's okay. Good. Yeah. So I am extracting these from this PMNS matrix. I am extracting the solar mixing angle and reactor mixing angle, solar mixing angle, atmospheric mixing angle, and delta Cp. And these are the model predictions. So you have these analytical expressions. And of course, the neutrino masses, the ratios, again, that's coming from these eigenvalues. This is the full prediction, and this is the full table of the observations. This is again from the global fit, and you can see the red ones are the numerical values of the prediction I showed in the last slide, and this is the 1 sigma fit. So these three are really good agreement. The other one, atmospheric angle, is not within 1 sigma, it's within 3 sigma, but then the atmospheric measurement is still not that precise, and there are people are talking about the quadrant, which quadrant it is, and all those things. Yes. And this most important thing, I mean, the new neutrino experiments are trying to measure this delta Cp, and we predict a maximal delta Cp value for this. Okay. Okay, so maybe this, we are shifting to the next part of the talk. I don't think I can do that. So maybe I will give a simple um, direction towards what I'm doing there. That's all. So what I said earlier was that we had this 5A, 5B, 5C, and then I told you that trust me, these are going to be the minimum, right? You're just trusting me. But now I am trying to say that, well, they are the minimum. I can prove that they are the minimum. And this can be done using something called residual symmetry. So what are residual symmetries is that you have a field and you say, well, the field is transforming under some group, right? And then you say that the field is getting a minimum. You're going to fix the field to a minimum, that is the spontaneous symmetry breaking. So once you fix it to the minimum, then you cannot allow the field to transform because it's a constant value, right? But then that constant itself remain invariant under certain subgroup of the original group, and that subgroup is called a residual subgroup or residual symmetries. So each of these minimum that I wrote here, this value and this value and this value, they have their own residual symmetries. And for the first case, I am noting here. So the first case, the alignment is 1 tau, right? I mean, this other one is just some constant. That doesn't matter much. So alignment is 1 tau, and this is an element of the group. So if you act this will remain 1 tau. And another element of the group is this and conjugation, because conjugation itself is a part of the group, because I've introduced CP. So conjugation also is a part of the group. So this star and this is a group action, and it will remain invariant. So these two guys, it generates the residual symmetries of the original group. And that group is called a Klein 4 group. So in this particular case, it is Klein 4 group. And why is it important is that in this my paper, which also uses a lot of results from these math papers, in these works, I showed that if a particular alignment, if every degree of freedom of the alignment is determined by its residual symmetries, then that alignment is guaranteed to be a stationary point of the potential. So this is kind of result. It's not just my result. It is some there are mathematics papers which sort of get to this result. So I have just used it in this physics context. So in this case, I am here showing that this particular alignment is fully determined except this constant. Again, as I said, the constant doesn't matter much. So otherwise, the alignment is fully determined by residual symmetries. Therefore, with that mathematics theorem, you can show that this alignment is guaranteed to be a stationary point. When I'm specifying it's a stationary point, because I'm not saying it's minimum, because stationary point can be something like saddle point, etc. So those complications exist. So I have to show that specifically this is a minimum. That is another job, but I'm not going there. And you can do the same experiment for the second field also. So this is the field, and I am showing the residual symmetries of that field. And you can show that these residual symmetries fully determine the alignment. Therefore, by the math theorem, this alignment is guaranteed to be a stationary point of the potential. And the same for the last case. So what I have shown here is that if you individually write the potential of the first field, you will get that minimum. If you write the individually write the potential of this field, you get this minimum. For the third field, you get that minimum. But then there is still the other problem. What about the cross couplings? So first we'll couple with the second, second with the first, and so on. So the cross couplings also have to be included. So that is the next part of it. So this, then it turns out that the cross couplings between phi A and phi B, the only cross coupling, I'm doing only
I,
renormalized.
we have 2 minutes left.
Okay, I'll just finish. So only these cross couplings exist, and it so happens that these cross couplings doesn't affect whatever I said earlier. That these are called they are harmless cross couplings, and this is also done in my paper here. So this paper actually investigates the cross couplings and see whether they are harmless or not, and I have derived this something called compatibility condition. So if the cross couplings satisfy the compatibility condition, then it means that those cross couplings are harmless. So whatever minimum that you have obtained, that will remain unaffected by the introduction of cross couplings. I think that's it. That I've talked about almost all the concepts. Yes, thank you. And maybe if you have some questions, I'll take from here.
Okay, thank you for the nice